Today is lecture 17. I don't like to really call it a lecture, but day 17 in here. I always look back over my notes when we're done with class to make sure that I did justice to the material that we were just covering, and I realized that I left one point out from the last section, so I'd like to start with that today on discontinuity. What it means if the authors ask us to do something with a problem that has removable discontinuity. So I had it in my notes, but I skipped over it, so let's go back to it. So this is really from section 2.4. On continuity. In what your authors refer to as a removable discontinuity. I talked about jump discontinuity and infinite discontinuity, lines and curves with holes in them, and we did that, but this is just a term I forgot to mention. So it refers to a line or a parabola or some kind of a curve with a hole in it, and defining in terms of a split domain function the way to, instead of being left with that hole in the graph, to fill in that hole. So the function might look something like this, and I'd like to kind of kill two birds here with one stone. I'd like for us to look at the difference of two cubes. I don't think that's come up yet in a problem. X cubed minus 1 cubed. And that's the definition of the function if the function is not 1. And then if we want to take that discontinuity that exists in our first description of the function that has a hole in it, and if we want to fill in that hole, what do we call the function when x is 1? So that's what we're seeking right now, is where is that hole in the graph, and what do we define y to be when x is 1 so that the hole gets filled in. So let's take this thing, x cubed minus 1 over x minus 1. We know if we put in 1 that we get 0 over 0, which is a problem, so that's not going to get us anywhere. Does everybody agree that the numerator factors? Can we get agreement on that? Now, can we also get agreement on that you know how to factor the numerator? Not quite the same agreement there. But you know it factors, right? And you know it factors into x minus 1, some binomial and a trinomial. By the way, how do you know, absolutely know, that x minus 1 is a factor of the numerator?
You just know.
There's a hole.
Good answer.
How do you absolutely know? There's a called, I'll just give you the name of it, you can tell me what it says. The factor theorem or the remainder theorem. There's really two of those. Either one of those will suffice.
I got you.
Why does x minus 1 absolutely have to be a factor of the numerator? Because 1 is a root of the numerator, right? If I put 1 into the function and it gives me 0, doesn't that absolutely guarantee that x minus 1 is a factor? So it's got to be a factor, and the question is what is the trinomial? There's a hint that I might multiply by the binomial x minus 1, and the end result is x cubed minus 1. Part of it you can figure out. Doesn't there have to be an x squared here? Mm-hmm. Because the x times the x squared then will give us the x cubed. So it's got to start with x cubed, and it's got to end with what?
Plus
1.
Minus 1. So we've got to have a plus 1 here, right? Mm-hmm. And the only question is then what's that middle term? Somebody just said it, I believe. Minus x? Close.
Plus x.
Plus x. Now, let's say that, not that this was true for any of you, but let's say you just draw a blank on, that's hypothetical, right? That you draw a blank in how to factor the difference of two cubes. So you know that I've got x cubed, and I'll just put the minus 1 out there because I know I'm missing an x squared and an x, so I kind of left some space for them. and I know I'm dividing that by x minus 1. Isn't that what we're doing? Trying to find the quotient of x cubed minus 1 divided by x minus 1. First piece we already have x squared, or if you don't know that, then you basically, how many times does x go into x cubed, right? Polynomial, long division. So then it's x squared. X squared times x is x cubed. X squared times minus 1 is minus x squared. And in long division, what do you do with the stuff that you bring down? Subtract it. X cubed minus itself, that was the intent, to get rid of that. 0 plus x squared is x squared. And now let's go again. How many times does x go into x squared? X times. X times x is x squared. And x times minus 1 is minus x. Minus, what did I say? Minus x and wrote down minus 1? Okay, let's do that again. X times x is x squared. X times minus 1 is minus x. What do we do with that? We subtract it. So we get 0x plus x is x. Bring down the minus 1, and then we're in business, right? How many times does x minus 1 go into x minus 1? 1. So there's our trinomial. So anytime you forget how to factor the sum of two cubes or the difference of two cubes, you could always use long division. So I'm coming back to here. I'm going to rewrite this down here. That x cubed minus 1 over x minus 1 Everybody all right with that? So as long as x is not 1, here's the original problem. Here's our f of x. So we're trying to deal with this hole in the graph and then remove the hole in the graph by assigning y to be something when x is 1. So as long as x is not 1 in this first line, this over this reduces. That's some number over itself. It's not 0 over 0. And we're left with x squared plus x plus 1. Not that we have to do this at this point in time, but isn't that a parabola? Right? We could find the vertex. We could enter it in on our graphing calculator. We could sketch this somehow. But isn't it a parabola with a hole in it? It's a hole in it where? And that's the key to this removability issue. At x equals 1, y equals?
0. What? Y equals
Okay, now
1.
remember we reduced. There's what we're left with.
3.
If x could have been 1, what would y be in what's left?
3.
It'd be 3. Everybody all right with that? Be 1 squared plus 1 plus 1. So this is a parabola with a hole in it. So the hole is at the point 1 comma 3. X can't be 1, therefore y can't be 3 from our first line. So if we want to take that hole in the graph, or discontinuity, and now remove the discontinuity, I'll assign y to be what when x is 1? 3. So I've taken what was in the first line and was a hole in the graph, a discontinuity, and in my second line I've removed that discontinuity. Now what's a way of taking that split domain function and rewriting it in a whole lot simpler terms? Wouldn't it be this? The whole parabola, right? The parabola without a hole in it. So that's the same thing as f of x up here. This f of x and this f of x are the same thing. I've taken the discontinuity that existed in the first line, removed it with the second line. It's the same thing as the whole parabola. So I forgot to mention the removable discontinuity, but that's the kind of problem where we take the hole in the graph, basically, and reassign y to be that y value when x takes on that so-called bad x value. Is that okay? That's really from 2.4 and continuity and what constitutes removable discontinuity. Okay, the new material, limits involving infinity. So we want to see what happens. We want to examine certain types of functions when the y values are going to infinity. And then we want to examine certain situations where we're allowing the x values to go to infinity. What happens to the y values? So we've got all kinds of problems centered around those two basic ideas. So the first topic that the authors address is, let's examine some functions where the y values go to infinity as x takes on certain x values. So we know what causes that. Let's take a look at a simple function where the y values are going to infinity. And in fact, where does that happen on this particular picture?
3.
X equals 3, right? In fact, isn't 3 a bad value, a value that we can't use at all?
Mm-hmm.
So x cannot be 3. So we know what the picture looks like. So we come out here with a vertical boundary. And for values larger than 3, what do we get? Positives, right? 1 over a positive number. So we're coming in here with the graph. And for values less than 3 that we put in for x, we've got 1 over some negative value. So near 3, this is the line x equals 3, which we recognize from previous math courses as a vertical asymptote. The graph is the y values are going up toward positive infinity and toward negative infinity. Well, the corresponding limit problem that we need to concern ourselves with, actually there's 3 problems here. And we've already dealt a little bit with this, but the authors take this situation, and what's the answer to this? What's the limit of this function as x approaches 3?
Does not exist.
Does not exist, right? Or no limit. So we've already addressed that, but they elaborate on that a little bit, and this is difficult for me because I have a hard time saying that the limit is infinity or the limit is negative infinity. That doesn't seem to want to all roll out of my mouth in the same sentence or phrase. When they do that, they're talking about what's happening to the y values as the x value approaches, in this case, 3. They're not really saying that the limit is infinity. So we know this answer to be does not exist. We also know this answer. That's the two-sided limit. Let's take a look at the two one-sided limit questions individually. I have a hard time even writing this down.
Negative.
But they're going to refer to this as having an answer. I think the best answer for us to say is that there is not an answer. I still believe that, and I think your authors still believe that. But for graphical or geometric reasons, if we want an idea what happens to this function as x comes closer and closer to 3 from the left, I have a hard time with this. They will say that it approaches negative infinity. That's not the best answer. The best answer is does not exist. And what happens as we come in from the right? positive infinity. Again, the best answer is there is not a limit, but this is just for descriptive purposes. And in fact, they have a disclaimer in your book, and I copied that disclaimer so you can know that why I'm having so much difficulty saying the limit is negative infinity or the limit is infinity. This first statement up here, this does not mean that we are regarding infinity as a number, okay? And if it doesn't have a number for an answer, it's not supposed to have an answer, right? So we're in agreement there. Nor does it mean that the limit exists. The limit does not exist. So that you might be thinking, well, why are they saying the limit equals something? That's my question too. It simply expresses the particular way in which the limit does not exist. They used 1 over x squared, can be made as large as we like by taking x close enough to 0. Okay, or we could get smaller and smaller and smaller values as we approach 3 from the left. We could get larger and larger and larger values as we approach 3 from the right. So there's the disclaimer from the authors. It's not meant to be a formal limit solution. The formal limit solution does not exist. But for descriptive purposes, it's okay to say it approaches positive infinity or negative infinity. Another thing your authors say here, which is a descriptive kind of a phrase, is that the function, the y values, increase without bound as x approaches 3 or x approaches 0. The y values decrease without bound as x approaches 3 or x approaches 0. So again, it's for descriptive purposes only. Okay, the first definition that you see here basically addresses that same issue. This is the notation that they're allowing to be used. The limit of some function is infinity. Still have a hard time with that. As x approaches a, means that the values of f of x can be made arbitrarily large as we want them to be, as we take x sufficiently close to a on either side of a, but not equal to a. So a lot of that stuff we've already addressed, the two-sided limit, how close do you get to a, but they're allowing the answer to be infinity for descriptive purposes. We've seen and used vertical asymptotes before. Now let's look at a definition or description of vertical asymptotes with regard to limits. So these two say what happens as x is approaching a. That means from both sides of a. So is it possible to say that if we know there is a vertical asymptote there, that the y values could go to positive infinity from both sides? That's possible. Could look like this. Right? Isn't that a picture that goes along with this one? Mm-hmm. That as we're closing in on that vertical asymptote, that x value that is the vertical asymptote, from both sides the y values could both be going to positive infinity. That's possible. They could both be going to negative infinity. Similar picture, both branches down here. So that's a two-sided limit could actually be approaching very, very large values from both sides or very, very small values from both sides. And then these are the one-sided equivalents. We could be approaching positive infinity from the left side, negative infinity from the right side, or the reverse of that. So we could, I've got the wrong pairing there, don't I? Well, it is possible from the left side of A to be approaching positive or negative infinity. May not be exactly what I just said. And it is possible from the right side of A to be approaching both positive and negative infinity. Not on the same graph, obviously, but on different graphs. So the rest of these, this is possible. We've seen that to be true. We just saw that to be true. This is also possible. So any of those scenarios tell us that what? X equals A is a vertical asymptote. Graph is completely undefined, and this will get me to my next question. Is it possible, ever possible, to have a graph where a point is plotted in a vertical asymptote? Never possible. In fact, the function is completely undefined there, right? You'll never, absolutely never, plot a point in a vertical asymptote. Now, the other question, you say, well, that was a stupid question. What'd you ask that for? Obviously, you never plot a point in a vertical asymptote. That's why it's a vertical asymptote. The other question is it ever possible to plot a point that is in a horizontal asymptote? And the answer is yes. That is possible from time to time. But the vertical, the function is completely, absolutely undefined. So you never plot a point. A horizontal asymptote is only good for x's that are approaching infinity. And that's the next point, is dealing with horizontal asymptotes. Let's get this last piece right here. This is for descriptive purposes only. If we wanted to analyze what's going on a natural log function, as x approaches 0 from the right, well, x can't approach 0 from the left because the graph doesn't exist over there. Let's just see what a natural log graph looks like. Doesn't it look something like this? Right? So what happens to the y values as x approaches 0 from the right? What's happening to these? Aren't they approaching negative infinity? So that's just a description of that, not a formal limit statement. Just says the y values are getting infinitely small as x approaches 0 from the right. So that's kind of the author's treatment of when the y values are going to infinity. So these are all kinds of limits involving infinity. So the answer here is infinity. Now let's see what happens as we let the x values approach infinity. And a whole variety of things can happen here. So we want now to focus in on what happens when the x value is approaching infinity. So now we kind of switch horses, and we're not talking about a vertical asymptote anymore. We're talking about a horizontal asymptote. What y values are we getting closer to as x approaches huge numbers way out to the right? So let f be a function defined on some interval. Then the limit of f of x is L as x approaches infinity, means that the values of f of x can be made as close as we want to L based on how close we get to infinity. So we know these to be, from previous experience, we know these lines, these y equals L lines, to be horizontal asymptotes. And therein lies, backing up to my previous question, can you actually plot a point in a horizontal asymptote? Yes, you can, because they're only valid for what kind of x values? Large x values. So if x is reasonably small, I don't know what small means, but if x is reasonably small, it's certainly valid for you to plot a point there. But as x goes way out to the right, eventually it approaches that line, that horizontal line, as a boundary. Okay, we'll come back to some of these. Let's look at some different situations of what can happen with different functions as we allow x to approach infinity. So we're going to let x approach infinity. Let's see what happens if we take a function. Let's just start pretty simple here. What happens to the function 1 over x as we allow x to get infinitely large? Kind of a baseline limit for you to remember, and it comes in handy on a lot of different problems. 0. Does that make sense? As you make the denominator larger and the numerator is fixed, when the denominator wins, so to speak, it gets larger, and the numerator is fixed, eventually you've got 1 over 600 trillion. If that's all the money you have in your pocket, you're not exactly very wealthy, are you? 1 over 600 trillion dollars. I don't think you're going to get a very good lunch when class is over today. So that's, as x gets larger and larger, this thing approaches 0. And in fact, it doesn't matter what the numerator is. Could the numerator be 4? Same answer? Could the numerator be 400? Yeah, it does. The numerator could be 400 trillion. Wouldn't the denominator eventually win? Yes, and when that happens, the value of the fraction, if the numerator is, it can be as large as you want, but if the denominator eventually gets larger and larger and larger, the value of that fraction approaches 0. Now in this case, does it matter, can we approach infinitely large numbers, but they have a negative sign in front of them? Does that change this answer? Is 1 over negative 600 trillion also very, very close to 0? Yeah. So in both cases, we're approaching 0 way out to the right in this graph and way out to the left in this graph. Now, what's the picture y equals 1 over x? What does it look like? Well, we know it's got a vertical asymptote here. It's undefined at x equals 0. And when the x's are positive, don't we get positive? And when the x's are negative, we get negative. So aren't we over here? When the x's are positive, because there's a vertical asymptote at 0. Now, can't we complete this picture by saying that eventually as x gets large, what happens to the y values? They approach 0, and as x approaches negative infinity, what do the y values approach? They also approach 0. So from the previous stuff, we have a vertical asymptote which says the y values get infinitely large and infinitely small on either side of x equals 0. This says that if we allow x to get infinitely large, the y values approach 0 way out to the right and way out to the left. So we've got that horizontal asymptote as well. Horizontal asymptotes for the function, let me put a couple of different pictures here. Let's say here is our limiting value. So that's L, the line y equals L. If the limit of the function is L as x goes to infinity, that just tells me that eventually, way out there to the right somewhere, my picture has to get closer and closer and closer to that dotted line. So is it possible that I could come in here and cross the asymptote and then approach it from this side? That's certainly possible. It is possible to have a point that's plotted. Here I've got 2 points, right? 2 points that are plotted in the horizontal asymptote. That's completely legal. Because, well, you tell me, when is the horizontal asymptote a true boundary for what kind of x values? Large, right? So for x approaching infinity, that means way out here to the right, it serves as a boundary, but not necessarily in here. So how many times can you cross the horizontal asymptote? Many as you want to. It is possible for a graph to look something like this as well. We could have this limiting value, this horizontal boundary. You could have some kind of an oscillatory function that continues to cut through here, and each time the amplitude of that function is a little less and less. Now, is that still true, that we are approaching L as x moves out to the right? That's also true. Still true. But we're crossing that horizontal boundary numerous times. But we're getting closer and closer to it, above it and then below it and then above it, below it. But as we go above and below, they get closer and closer and closer each time as it progresses. So that would be like a decaying amplitude, right? The amplitude is decaying as it progresses. So that's certainly possible. Now, we're not going to deal with a lot of functions like that, but it is possible. Umair.
But how can a line pass through asymptote? How could it cross an asymptote?
Because, back to the definition, it's only valid for x approaching infinity. So are these values, I guess this is the question you have to ask yourself, are these values close to infinity?
Yes.
Not really.
I mean,
If you have $5, that's a lot of money. It'd be a lot of money for me to have. But is that close to, $600 trillion? It is $600 trillion. Is that even close to infinity? No. So the horizontal boundary is a different kind of animal than a vertical boundary. A vertical asymptote is an absolute, never to be crossed boundary because the function is completely undefined there. Horizontal asymptotes are just a different animal. It's allowable to cross. It just says that as we allow x to get larger and larger, we eventually approach L. How we approach L can happen a lot of different ways. Either side, it could just do most of the time we see things like this. Doesn't the function do something like this, nice and clear, and it just kind of approaches it from the bottom, right? We see that a lot. So, and we're going to see more of that than we see of this. But it is possible to oscillate with the decaying amplitude and approach it from either side. Okay, here's some functions that we ought to know what they look like so we can analyze these limits. Let's say our function is inverse tangent. Without a calculator, could you sketch right now in 30 seconds or less, could you sketch the inverse tangent function? That was some interesting looks. But I remember I have a 15-year-old, so I get all kinds of looks. Okay, let me do this. Could you, if this were the function, how many of you in 30 seconds or less could graph that? Okay, everybody, right? So let's see what this looks like. Doesn't it have a problem at pi over 2? Mm-hmm. And then a problem at negative pi over 2? Everybody all right with that as kind of a one cycle of the tangent function? Period is pi, right? Doesn't have any amplitude. So what's the relationship between the tangent, which all of you seem pretty familiar with, and the inverse tangent? I just have a hint there, a big hint in there. The relationship between the tangent and the inverse tangent.
Switch it.
They are what of each other?
Inverse.
Inverses of each other, right? That's why it's appropriately named the inverse tangent. So if we can graph this, and these are nice little vertical boundaries, what do these nice little vertical boundaries become on the inverse? Little horizontal boundaries. So we'll come up here to pi over 2. And down here to negative pi over 2. There's our boundaries. 0, 0 is its own inverse, right? So it's on both. Does that seem right for what an inverse tangent should look like? And we could plot some points, but I mean, if you just take that and kind of lean it on its side there, I think you'll see that this is an inverse tangent and this is a tangent. So let's see what happens on the inverse tangent. I'm going to go ahead and say positive infinity here since I want to go the other way. What happens to these y values as we allow x to get infinitely large? What are we approaching? Pi over 2. Everybody all right with that? What happens to these y values on the inverse tangent as we allow x to get infinitely small? Negative pi over 2. So if we have a good familiarity, which I think you do with the tangent, let's just kind of rearrange the x's and y's, get a picture of the inverse tangent, and we can do limit problems. Now, does that mean that y equals pi over 2 is a horizontal boundary? Yeah, it is for part of this graph, isn't it? It's a horizontal boundary for large x's. Negative pi over 2 is a horizontal boundary for infinitely small values of x. Okay, I bet you these situations you have dealt with before, and you may in fact know a shortcut, so you can tell me and the rest of the class what that is. Let's say we want the limit of 2x squared plus x minus 3 over 3x squared plus 11x plus 4. Way out to the right. Answer? Zach, you said it.
2/3.
2/3. How many of you were thinking that? Anybody else?
Almost got it.
Okay. Can you remember what the shortcut is?
Just use the two coefficients.
Okay, the two lead coefficients. Does that ring a bell? When can you do that? Okay, when the exponents are equal. So I think we just resurrected that shortcut. So if you look at this, and x is getting infinitely large, that's got to be that type of limit, and you've got something with like degree, numerator and denominator, in this case x squared over x squared, the final limit answer ought to be the quotient of the lead coefficients, which it is. Now let's suppose that several of you in here forgot that. Not that that would ever happen. But what's a backup process that's going to work on all of these limits?
You divide.
Zachary. Right? No.
Equally. It's Zachary.
Zach.
Yeah.
Okay.
You divide all the numbers by the highest, by the x with the highest power,
Okay.
and then you.
And I like that better, in fact, what he just said than what's in the book. I like it dividing through by the largest power of x that you see in the problem.
And then you got constant over x is 0 when x
Okay.
goes.
So let's do what he said to do. This will work on any limit problem of this type. So when in doubt, divide through by the largest degree of x that you see in the problem. So we're going to kind of delay here the allowing of x to approach large values. Let's see what we get when we simplify. 2x squared over x squared is 2. X over x squared is 1 over x. Minus 3 over x squared, we're kind of stuck with that. 3x squared over x squared is 3. 11x over x squared is 11 over x. 4 over x squared, we're stuck with that. Now let's allow x to approach infinitely large values. Does that affect 2 in the numerator? It doesn't have any x in it anymore. It's unaffected by x. Same with the 3. What happens to 1 over x as x gets huge?
0.
That gets small. How about 3, actually negative 3 over x squared? Doesn't that get really small as x approaches infinitely large values? Same thing, 11 over x approaches 0, and 4 over x squared. It's very, very small, so we're left with what Zach said earlier, 2/3, right? So if it's the quotient of two polynomials of like degree and x is approaching infinity, look at the lead quotient of the lead coefficients. Now there's some other shortcuts too in this type of problem. Let's suppose that the degrees, any question on this before we cover it up? Lisa?
So you can use, if the exponents are not equal, you can use the second example, what you just did.
Right, and in fact, but there's a shortcut there too. That if you choose to memorize the shortcut, that's fine, but if you choose not to, that's fine also. So let's say degree of the numerator is 2. Degree of the denominator is 1. Guesses? Let me ask another question first. Which wins, the numerator or the denominator?
Numerator.
The numerator wins. And by winning, I mean it gets larger, right? Faster than the denominator. Be nice if the denominator won, because we could say, we know what happens to fractions when the denominator wins. They get smaller. When the numerator wins, that fraction can just get larger and larger and larger, can it? So what would be your guess?
1.
2? 1? So that means a lot of you are not saying an answer because you don't think the limit exists, right? Right? I'm in agreement with you that it doesn't have a limit. When the degree of the numerator is larger. Now let's go back to our backup.
Oh, yeah. 0.
Now you'll see something a little different in your text. It works also. They say to divide through by the largest degree of x that you see in the denominator. That's fine, that would work, but let's make it simpler. Let's just divide through by the largest degree of x that you see in the problem. So we'll delay the fact that x is going to approach infinitely large values. 2x squared over x squared is 2. X over x squared is 1 over x. 7 over x squared, we're stuck with that. Down here, x over x squared. Aren't we stuck with a problem in the denominator? Is that right? Got a nice little 2 in the numerator. This goes to 0, this goes to 0, this goes to 0, and this goes to 0. So there is no limit. And if you think about it, if the numerator gets larger and at a faster rate than the denominator, I mean, this keeps getting larger and larger and larger, doesn't it, in size? Look at a series of numbers. If you go 6 over 2, and then the numerator goes to 10, and the denominator goes to 3, the numerator goes to 28, denominator goes to 5. Well, they're both getting larger, but the numerator is getting larger at a faster rate. Are we closing in on any one specific number? For goodness sakes, no. I mean, that just keeps getting larger and larger and larger, so it makes sense that whenever the degree of the numerator is larger, it doesn't matter how much larger, than the degree of the denominator, and x is approaching infinity, there is not an answer. You should not be expecting an answer. And what's the situation then, the other one, when the degree of the denominator is larger? Do I need to write it down?
0.
Just take this thing and flip the top and the bottom. What do you get?
0.
0 over 2. What's 0 over 2, or 0 over 7, or 0 over 15 is 0. So when the degree of the numerator is smaller, we've already seen a problem like that. We looked at this. Right? Isn't the degree of the numerator smaller? That's degree 0. The denominator is degree 1. So the limit of that would be 0. So it can be as quick as that. If you look at the problem, they have the same degree, numerator and denominator. X is approaching infinity, coefficient over coefficient, right? You look at it, the degree of the numerator is less, x is approaching infinity, end of problem, the answer is 0. So if you remember them, fine. If you don't, you've got this as the algebraic procedure that will work kind of in the background. Okay, let's go to a trig function. Try to picture the cosine graph and then move out to the right. Just keep letting x get larger and larger and larger. What happens to the y values?
Approach.
Don't they just oscillate between one?
Okay, yeah, they oscillate, don't they? Don't they? Aren't they kind of stuck between 1 and -1?
Yeah.
So the graph is this, right, as we go. So are we approaching any one specific number as we go out there to the right? No, it just continues to oscillate between 1 and -1. So the answer is does not exist. Now that comes in handy occasionally on a limit problem, is that we know how the cosine is behaving in a sense that we've got it trapped. It's somewhere between -1 and 1, then maybe we can analyze the other piece in the problem. But the cosine or the sine, neither one has a limit as x goes way out to the right. Okay, let's see what happens here. I think we've already dealt with this issue. Let's see if we can give two answers. One, which is a realistic formal limit answer, and then another one which kind of describes what's going on the graph.
Would it be does not
Does
exist?
not exist.
Okay, the best answer, the formal limit answer is does not exist, right? But for descriptive purposes, can we decide what's going on with the y values? Are they going way up to positive infinity, or are they going way down to negative infinity?
Positive infinity?
Okay, you're putting in infinitely large positive numbers, right? What's the SIGN of the numerator? What's some huge number squared minus that huge number?
Positive?
Positive, right? And down here, what's 5 minus some tremendously large positive number? Negative, right? So if we wanted to give a descriptive answer to this, after today we won't be giving a whole lot of descriptive answers because I don't, it's bothersome to me to say the limit is infinity or negative infinity. What might we say for a descriptive answer? Negative infinity. Now, which would be accepted? It kind of depends on the nature of the question. If it's just a limit question, does not exist is the best answer. But if I would say something like, for descriptive purposes, what is actually happening to the y values, then you can say they're approaching negative infinity. Okay, let me take a quick look at this and see if I've covered everything that I wanted to. All right, I think we did. But if we didn't, and I look at this a little more thoroughly, then we'll just start with that next time. I've got some problems here from the text. You knew that, didn't you? Mm-hmm. There are some great problems. I mean, some really good problems in this set. I had a hard time narrowing it down to 13 or 14 problems. In fact, there's a couple of these that we absolutely have to discuss in class. And that finishes lecture 17, and I will see you tomorrow. I think tomorrow we'll start with your questions, so when you come in tomorrow, before we actually start on the cable broadcast, just tell me what we need to look at and how much.
Taking up our homework today?
No, I've got to get these other ones back to you before I pick up any more.
Like
this written down. They have the same X degree talking about this here.